Hey guys, we're going to finish up talking about lesson 3.1 today. If you remember from last week when we were doing 3.1, we were talking about the derivative. And we had this definition of the derivative as the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, remember the derivative tells us the slope at any given point. Okay, so whatever point x we're at, this would tell us the slope of that. Now you don't need to write that down, it should be in your notes from last week. There is an alternate form of this, and it's the alternate form of the derivative, and it looks like this. The derivative of f at c is the limit as x approaches c of f of x minus f of c over x minus c. Here's where this comes from. So suppose you have this curve, and we want to find the slope at this point C. So this is the point C, f of C. Okay, so the way we're going to get that slope is we're going to pick another point on the line. We'll call it point X. So this is X, f of X. And we'll find the slope of the line between those 2 points. Okay, and that'll give us our derivative. So this distance here is just x minus c. And this distance here is f of x minus f of c. And we're trying to find the slope between that. So we take the change of y over the change in x, which is exactly what we have here. F of x minus f of c over x minus c. Now, to get a better and better approximation of this slope, we're going to take our point x and move it towards c. So that's what this means. Okay, the limit as x gets closer and closer to c of this slope that we're finding, that is another way that we can do the derivative. I'm going to get rid of all this scribbles. Okay, so it's just another form that is sometimes helpful, and we're going to be using it in the next couple examples. Now, in order for the alternate form to work, the one-sided limit from the left and the right have to be equal. Otherwise, this just doesn't work. Now, one other thing that we need to talk about. If a function is differentiable, that means it's continuous. Okay, that's just kind of a given. However, you might have a continuous function at a point x equals c, but it's not differentiable. So being differentiable means it's continuous, but being continuous does not necessarily mean differentiable. And I'm going to show you a couple examples of that. So in 6, we've got this function. It's an absolute value function. So absolute value, of course, is a V shape, and the minus 2 moves us to the right 2, and there's our absolute value function. So first of all, is this continuous? Well, yeah, it is. There's no holes, there's no asymptotes, there's no jumps. So now what we're going to do is we're going to look at the derivative at 2 from the left and the right. Now we're using the alternate form here. Okay, so I'm looking at the derivative, the slope, as we approach 2 from the left. What's the slope of that line as we approach 2 from the left? Okay, so here's our alternate form, f of x minus f of 2 over x minus 2. So we're approaching 2 from the left. F of x is our function, minus f of 2, that's just if we plug in 2 to our function, which is 0, of course. So we get the limit as x approaches 2 from the left, the absolute value of x minus 2 over x minus 2. Now, we can think this through. We don't even need a calculator for it. We're approaching 2 from the left, which means we have something slightly smaller than 2, like 1.99. Now, when we plug in 1.99 in the numerator and the denominator, they're both 1.99 minus 2. So we're going to get the same thing in the numerator and the denominator. The only difference is going to be what the signs are. So in the numerator, we plug in 1.99, we subtract 2, we get some number, and then we take the absolute value of it. So this is a positive number. Then in the denominator, we take 1.99 minus 2, and we get the same number that we did in the numerator, except this one's negative, because remember it was 1.99, we subtracted 2. So when we take a positive number and that exact same number, except it's negative, and you divide those, you're going to get 1, negative 1. okay, which we can already kind of see. Remember, we're looking at the slope as we approach 2 from the left. Well, the slope's -1. Okay, now we need to look at it from the right, okay? So now we're going to approach 2 from the right. Maybe you can already see what the slope's going to be. Let's hope so. I don't know what just happened. Sorry, I was scrolling out of control. Here, let's try this. There we go. Okay, let's look at it from the right. So f of x is still x minus 2 minus f of 2, you just plug in 2 and you get 0, over x minus 2. Oh, there's no absolute value there. Sorry. Okay, so this gives us the limit as x approaches 2 from the right of the absolute value of x minus 2 over x minus 2. Okay, same thing. Now we're approaching 2 from the right, so something like 2.001. So we plug in 2.001, we subtract 2, we take the absolute value of it, we get a positive number. On the bottom, we take 2.001, subtract 2, we get the same number, and it's positive. So since we have the same number on top and bottom, and they're both positive, this is going to be 1. So back on our graph, the slope, as we're approaching 2 from the right, is 1. Okay, so what this means is since those are different, the derivatives are different approaching from the left and the right, that means at 2, this is not differentiable. Okay, and actually any graph that has a sharp turn like that, like an absolute value graph, it is not going to be differentiable at that turning point. In the next video, we will take a look at one other function.